Hey guys, so in this video I want to expand on what we've been talking about with the inner product and function spaces, and then I want to talk about orthonormality in this function space, right? And before I talk about orthonormality in function spaces, I want to review orthonormality in the vector spaces that we've had before. So we're the regular Hilbert space where we had these discrete vectors. Right, so to do this, I'm going to define u and v as these vectors, right? This should be familiar, the superposition. And then in general, psi is c1 phi1 plus c2 phi2, which is the sum over all values of j, cj phi and our orthonormality condition is the inner product of phi m and phi n is this Kronecker delta function, right? And this delta mn is 1 when m is the same as n, right? 1 when m equals n, and 0 when m does not equal n, right? And this Kronecker delta, right, actually gives us two very important properties, right? And the two things it gives us, and I'll show you how it does that, and then we're going to expand this and figure out what our orthonormality condition has to be in function space in order to get the properties that we want out of the inner product. So the first thing is that u1 star v1 plus u2 star v2, right? That's what we want in the inner product. That's only possible, right, because of this delta mn, because this is not a dot product, right? We're literally, I mean, we're just taking the Hermitian conjugate of one and multiplying them, and because of the orthonormality condition, we get this expression that seems a lot like the dot product, right? And how you do that, right? I just had the bra vector u times the ket vector v. You rearrange the multiplication, you FOIL it out, right? These are just two terms, but you can easily see how this can generalize to more than two terms. And then whenever we have this phi1, phi1, right? Well, this is 1, right? But anywhere we have phi1, phi2, this is 0, so this term goes away, right? Phi2, phi1, this term is 0, it goes away. This is 1, right? So we're left with u1 star v1 plus u2 star v2. Using the same logic, we can show that all the terms where, you know, the subscript on u and the subscript on v are the same will stay, right? And so we'll have u1 star v1 plus u2 star v2 plus u3 star v3, etc., right? And so that's good. That's one thing, that this orthonormality condition. Hopefully you see where we use this orthonormality condition to get this result. Second, right, is that, and this is from our, I believe I called it our probability postulate, right, that we have phi k in a product with psi, and we want the coefficient of k, right? This is, which is the, the norm squared of this is going to be the probability of finding q, if you measure the quantity q, finding q equals k, right, is the norm squared of ck. So, or that q equals q sub k, right? And so how we would show this, right, is we just, all we have to do is we have to take this bra vector phi k and multiply it by psi, which I have over here, right? And then we can sort of bring the c1, because it's constant outside of that inner product, and so we get something like this, where c1 times the inner product of phi k phi1 plus c2 times the inner product of phi k phi2 plus dot dot dot, right? Which is just the sum over all possible values of j, cj, times the inner product of phi k phi j. But this is 0 if j does not equal k. So the only term, right, that will end with is this ck term, right? Because if, say, k is equal to 1, then this term is going to be 1, we'll have c1, and then every other term is going to be 0. Say k is 2, this term will be 1, this term will be 0, and every other term will be 0. If it was 3, then these two would be 0. Our next term, c3, phi k inner product with phi 2 or phi 3 would be, right, that would be c3. Every other term would be 0, right? And hopefully this, seeing how you can sort of change this into ck, bringing this out, right, and then this sum being equal to 1. That reminds us a little bit of the Dirac delta function, which brings us into the next thing that we are going to be doing. So hopefully you have those down, because now I'm going to sort of do the analogy to that in continuous space. And now I want to start with an apology for the confusing subscripts that I'm going to have in this video. I have been working this out on paper as many different ways as I could, and there was no good way of doing this without a ton of confusing subscripts. So I'm sorry, just try to go slow, keep track of what I'm doing here. In general, what I'm going to be having is Q1, and Q2 are all going to just represent like a general value, right? So it's not any specific value. Q sub k, which is sort of how we used it last time in like a few minutes ago, right? This is going to be a specific value, right? Uh, and so that's sort of like, when we're summing over k, that's sort of, I'm using these sort of how we've used j. If this doesn't make sense, it will in a second, but I just want to define this so we can see it easier. So first, let's define. Well, let's write out sort of the definitions that we had before. We have we have psi of x. We know is the integral from negative infinity to infinity of CQ times phi q of x dx, or sorry, not dx, dq, right? And I'm going to write this in a slightly different way that you will see. I'm going to write it in our bracket notation, where I have this ket state. It's not a vector, but it's a state. Psi of x is the integral from negative infinity to infinity. CQ, and this is phi q x dq. Right? So this is how I'm going to be writing it. And then I'm going to define two other functions. I've got psi1 of x. And I'm going to leave off the of x's from now on, just to keep things looking nicer. I'll put it in here. First of all, this is C1 of Q1. Okay, which is important. So let me rewrite that. I didn't mean to erase the whole thing. This is slightly bigger than I thought it was. There we go. So we have C1 sub Q1, right? And then phi sub Q1 of x dQ1, right? Where I just want to specify there's a difference between the q that I'm summing over in this integral and a q that I'm summing over in this integral, or that I'm integrating over. I'll leave the negative infinity here. There's a lot. I didn't mean to do that, but there's a lot of times that they'll actually not only just take off the of x's, and I'll leave the of x's in, but they'll take off the negative infinity to infinity, and they'll just write the integral and apply it. I don't usually like to do that, but I can sort of see why, because it's a bit tedious to write it every time. So we've got phi sub q2, telling you all these of x dq2. So this math seems a little bit tricky, and in all honesty, it is pretty tricky. But so try to just bear with me here. And there is actually a more formal way of doing this, but it requires a bit more like tricks with integrals, and I didn't want to do this, but I thought that this way was pretty sufficient in getting the point across. The one other thing that I want to write here is the ket vector, or sorry, the bra vector, phi1 of x, or psi1 of x, sorry, which is the integral from negative infinity to infinity. Just like how we had it before, we're going to take the complex conjugate of the coefficient, so c1 q1 star, and then instead of having the bra vector or the ket vector here, going to have the bra vector, phi q1 of x, still d q1, right? And so this is what we need to have. And now what I'm going to do is I'm going to throw out an orthonormality condition. Okay, that I didn't mean. I wanted to write the other part first. That phi m phi n. Actually, I'll say because we're dealing in the continuous space, I'll write it like this: phi sub qm inner product with phi sub qn, these are of x, but I'll leave that out, is equal to not the Kronecker delta, but the Dirac delta of qm minus qn, which again, the order doesn't matter because it's the same thing as delta of qn minus qm. Right? This is, I'm going to call our Dirac orthonormality condition, and it may seem like I sort of pulled that out of nowhere. And so now, what I'm going to do is I'm going to show you that this orthonormality condition, not the Kronecker delta, right? Because we're using integrals instead of sums, the Kronecker deltas won't do what we want them to do, and you can try to show that on your own. But instead of showing that, what I want to show is that the Dirac delta does do exactly what we want to do, and hopefully, maybe you can even see some of the deeper mathematical reasons of why this works. So the first thing, and I want to start with showing what we want the condition to be, and then I'll show that the Dirac delta does that, right? And so our first thing, right, we know that we want the inner product psi1 psi2 of x, but negative infinity, infinity. We want this to be C1Q star C2Q dq, right? Which is if Q is x, right? If the observable that we're taking the integral over is position, we know that Cx is the same as psi of x, right? Talked about that a few videos ago. So this will be the same thing as the integral from negative infinity to infinity of psi1 star psi2 dx. Right? And we showed this, I believe, in our last video, that this is sort of how we're going to define this inner product. Right. So this is sort of how we'll define our inner product, and this works. This is what we'd like it to show. And note that this works in any basis. The Q basis, the momentum basis, as we'll see, the position basis, any basis, it works. Right? And so this definition sometimes is a lot more convenient because we'll have psi of x, so we can do that inner product in the x basis because we have sort of these coefficients in the x basis because that's just the wave function. And so to show that the Dirac delta does this, I'm running out of colors here, so I'm trying to color code everything, but I'll use this red. So what I'm going to do first is, well, actually, pretty much the obvious thing to do will be, well, why don't I take the inner product of psi1 and psi2, right? Using our definitions here. So this will be the integral from negative infinity to infinity C1 Q1 star phi Q1 dQ1 times the integral from negative infinity to infinity C2 Q2 times phi Q2 dQ2, right? And now this is just something, and maybe you've taken multivariable calculus and you're familiar with this. If not, it's perfectly okay. So what I'm going to do now is this integral is independent of Q2. This integral is independent of Q1. So it's actually because of that, it's okay to combine these integrals and make this a double integral, both from negative infinity to infinity. And then at the end, we'll have dq1 dq2, right? And so what this is, this will be, well, C1 Q1 star, and then I'm going to push this a little to the side. I'm going to switch the order of this this bra vector and C2Q2. So C2Q2 times, and now hey, we've got the inner product of phi Q1 phi Q2, right? dQ1 dQ2. And as you know from multivariable calc, you're going to do this integral, then you're going to do the other integral. Actually, in this case, it does not matter which integral you do first. So this is a little bit of multivariable calculus. If you're not familiar with it, you can sort of just trust me on these steps, and you can see that there at least is a way of showing that this Dirac delta orthonormality condition is the right orthonormality condition for us. Right? Well, we're doing this integral, but we know that this integral, this is delta of Q2 minus Q1, right? And we've seen this kind of thing before, right? Well, we know we can take this, this is an integral dq1. We know we can take this thing with Q2 outside of the integral, right? But we also, this thing with the C star 1 Q1, it's 0 if Q1 does not equal Q2, and it's just C star, well, it's not 0, but this term is 0 if Q1 does not equal to Q2, right? So we can do the same trick that we've been doing and turn this into a 2 and then take it out of the integral. That's been our trick with doing integrals with the Dirac delta function. Hopefully you're understanding that trick, because as you see, we're using it in now like every video. It will get better. We won't be using it as much, but for right now, it's a very, very important trick when doing this integral, right? So what we'll have now is the integral from negative infinity to infinity, C1 Q1 star C2 Q2. Then we've got the integral from negative infinity to infinity. And actually then we can separate, we can bring this dq2 thing, this dq2, to that other integral, right? So we're kind of just swapping out terms using these tricks with the Dirac delta function. It's a very weird sort of calculus algebra thing, but it works. And every step here, they're tricky steps, but every step, I promise you, is a valid step with the math. And so then this is delta Q2 minus Q1 dQ1. Well, hey, this is the integral of the delta function. We know what this is. This is just 1, right? Right? And so now we're left with only this, because we're just multiplying it by 1. Right? And what you'll see is this is pretty much exactly what we want. Just instead of Q, we have Q1, but sorry, this is meant to be Q2. C1 sub Q2, right? Hopefully you caught that. So instead of Q, we have Q2, right? But there's no reason we can't just call that Q, right? It's all we're doing. This is just our sort of our dummy variable. It's what we're integrating over. We can call it whatever we want to, right? So this is just the inner product in the Q2 basis, right? So this will just be the same thing as, and I'll put that in here. This is the same thing as just saying, got the integral from negative infinity to infinity, C1 Q star C2 Q dq, right? We can call Q2 just Q, right? This is the inner product in the Q2 basis, inner product in the Q basis, inner product in the X basis. Whatever basis, it's all the same inner product, right? So, boom, we've got our one property, and the Dirac delta orthonormality. The trick was this integral, right? This integral being equal to 1. And you can actually see the way we did it before. The trick was the sum of the Kronecker deltas for all values of m and n. The sum of them is equal, or for all values of either m or n. The sum of them is all 1 because you're only going to have one term that actually exists, and it's 1, and everything else is 0. If that didn't make sense, that's okay. But so we're doing similar things. It's just when we replace the sums with the integrals, we have to replace Kronecker deltas with Dirac deltas, right? And that's how you go from a discrete space to a continuous space. But I still want to erase this first, and then I want to show that second property, that the Dirac delta does exactly what we want it to do in that second property. Also note here, because I showed Q and Q2, they're just general values that we're summing over, right? So our next property, and this proof will be shorter, we have that we want if I have phi sub q k, right, inner product with psi, I want ck, right? This is what we're looking for. So let's do this. So I've got phi qk times, well, psi is this right here in orange, so times the integral from negative infinity to infinity of cq phi q of x dq, right? And this is just a function of x and qk, right? And qk is different than q, right? And I used in the other one that q1 and q2 are not the same, right? They're just like summing over m and n individually. How we would have to do it when we like expanded that or the inner product, right, in the previous thing, and I'll pull that back up just to show you. When we expanded it here, as you can see, we're summing over all values, right? We could actually write this. We'd actually write this, and this might have been helpful to write. We could have written this as we're summing over all values of m and n of u m star vn times phi m phi n, right? That's really hard to read, but do you see that that's sort of what we're doing here? We've got we're summing over all values of m and n, and you can see we've got m equals 1, n equals 1, m equals 1, n equals 2, m equals 2, n equals 1, m equals 2, n equals 2, and so on, right? We'd have to have all of them. And that's exactly what we're doing here. What we did before, right? When we were summing over both Q1 and Q2, we were summing over them separately, right? Or integrating them over them separately. Okay, I just wanted to clear that up, just to sort of, yeah, just to clear that up. So and to show what we have here, I forgot to write this. This is phi q k inner product with psi. right? And now this is dependent on q, k, and x. This is an integral in q, so we can bring this inside. Negative infinity to infinity, cq, phi qk, phi q, dq, right? And now this is our delta of q minus qk, or whatever order you want to have it be, right? And when we do this integral, we've done this integral many times, right? Our trick is, well, hey, this is just the same as having that there, and bring it out of the integral, right? Because the integrand, this whole thing here, is 0 when q is not equal to qk, right? So it only matters when q equals to qk, and hey, we can bring that out of the integral, and now we are left with c sub qk. Exactly what we want. And so, this should show that the Dirac orthonormality condition, this one right here, this is the new orthonormality condition that we'll be using when we are in function spaces in continuous space as opposed to a discrete space. And I'll see you in the next video.